Hello, my name is Jansen Lee, and I will be presenting a demonstration of my doctoral research being performed at Vanderbilt University's Center for Rehabilitation Engineering and Assistive Technology in the lab of Dr. Michael Goldfarb. Today's video demonstration will feature a device we have developed called the Stance-Controlled Swing Assist, or SCSA knee. This device is indicative of our lab's more recent trends in the development of low-impedance assistive devices, and I will be showing it in use in just a minute. But first, I want to take a second to expand on what that idea is. As those of you within the field of prosthetic development know, the industry standard of care for individuals with a lower limb amputation is passive or modulated passive devices. In knee-based prosthetics, modulated passive devices can improve a user's ability to ambulate safely and effectively in daily living when compared to a fully passive device. When compared to research-based, fully powered devices, the swing phases of such modulated passive devices are generally characterized by notably lower impedance to movement from the user's perspective. This low impedance allows for what we have been referring to as inertial coupling between the user and the device. By this, we mean that the user is able to substantially passively influence the motion of the knee joint within limits through the actuation of their hip on their affected side. It is for this reason that users of modulated passive devices are able to perform so-called ballistic tasks such as level walking and the swing portion of stair descent reliably and safely. However, such devices leave the user fundamentally incapable of performing some non-ballistic unloaded tasks, such as the swing phase of stair ascent, walking up steep slopes, and recovering from gait perturbations. Fully powered prostheses can offer the full gamut of powered movements associated with locomotion, but design constraints often trade high torque generation for increased output impedance. The loss of the low impedance creates two fundamental challenges to designers. Decreased inertial coupling between the user and the device makes detection of user intent more difficult, and the user being inertially uncoupled can result in a gait in which the user may feel less in control and more along for the ride. The solution we have taken to both the inability of the MPK devices to add power into gait and the challenge of optimally controlling fully powered devices which do not couple inertially to the user has been a new, semi-powered approach to device development. Such devices, which include the knee which we are about to show, pair a high power density dissipation system, such as modulated hydraulic damping, in parallel with a low inertia, medium power addition system. By eliminating the requirement of the active drive system to perform high torque dissipation tasks, it can be downsized to minimize the added impedance felt by the user. In this way, the device allows for the user to be fundamentally in control during the ballistic and dissipative tasks at which the MPKs excel, but also results in a device which can add power to gait and allows the user to easily complete previously challenging tasks such as the swing phase of stair and slope ascent and recovery from perturbations. Additionally, this device is notably quieter and smoother than many fully powered devices that have been developed. And, as we will show, the inertial coupling is conducive to easy and robust intent detection, which we have not been able to achieve on Vanderbilt's previous fully powered devices. In the following demonstration, you will see me walking on the device using an adapter. The control is running in real time on the laptop carried by my colleague, but it does not require any inputs from him. In an attempt to better show the behavior of the device, I have included two consecutive takes shown side by side, one filmed from in front of the device, one from behind. In this demonstration, I will be performing three tasks: level walking, stair ascent, and stair descent. As you will see, to transition between level walking and stair ascent, I will simply tap my arm against my thigh on the prosthetic side 2 times at a frequency between 2 and 5 Hz while the prosthetic shank is near upright. To transition from walking to stair descent, I will simply tap the heel of my affected foot against the riser of the first step on my way down. And to transition from either task back to level walking, I will simply resume walking. Due to the ability of the knee to inertially couple to the user, their intention to shift modes is easily detectable in the sensor signals. Note that in the video you're about to see, all audio is unedited, and this is the volume of the knee during normal operations. So, without further ado, the demonstration footage.